Well, today what we will do is to talk about the aluminium production and the air pollution aspects associated with the aluminium production. If we really look at the process of the aluminium making, we can divide this in three parts. One is the mining, so let's write that. And we all know from our high school the ore for the aluminium making is bauxite. And once the bauxite is mined, it must be brought to a plant called, if I can divide this in three parts, onto something we call as the alumina plant. Okay, what we are really doing is that we are refining the bauxite. This bauxite comes to the alumina plant, and then we are essentially refining the bauxite in such a way that we can concentrate more and more of Al2O3. So refine the bauxite to form more and more of Al2O3 that we refer to as alumina. And once we have the alumina ready with us, then the next step is to take this aluminium oxide or alumina, as I said, to the process called electrolysis process. And what we do here is to produce the aluminium through electrolysis, and this process is essentially, if you can say that Al2O3 can go in the process of aluminium plus oxygen that will go to the this goes to anode, this goes to cathode, and the oxygen that will come out will go to anode. And what really happens as we go by, we will see in a moment. So if we go to the next board, okay, if you look at the bauxite, it is essentially Al2O3 which is hydrated. So let's write the hydrated part as some X molecules of water, plus it has lots of impurities. The impurities largely is Fe2O3, the iron oxide. It can have titanium, it can have silica in various complex form, it can have vanadium, it can have the gallium and various other metals. The process through which we like to enrich the alumina out of the bauxite is something we can refer to as the selective phase transfer. Okay, and we will see as to how the selective phase transfer is done. Okay, and this process of going through the selective phase transfer is also called as the Bayer's process. Okay, so what we will do now is specifically talk about the Bayer's process and as to how we can, out of all the things which are present in there, how we can produce from the Bayer's process, we can produce is very good quality, high impurity Al2O3. That's what is our objective, and we'll see in a moment as to how we can do it. It might be a good idea just to have a look as to where are the aluminium plants in India. So what you see here are those the rectangle boxes. You have a Hindalco, a large aluminium plant. You have National Aluminium Company in Orissa, that's again a very large aluminum plant. And we also have a plant called Balco, that is in Korba in Chhattisgarh. And then we have the other plants which is under the same name as Indal, as you see here. The part of it is in Hirakud, and another unit is in Aluminium in Kerala. And there is also a small plant, as what you can say as a Madras Aluminium Company, right in the Tamil Nadu. But India by and large are self-sufficient in aluminium production. In fact, the part of the alumina also we export to the different countries. But let's now go to the process flow sheet of making how the alumina is made. As I said in the beginning, there are three parts: the mining that we are not discussing in this lecture. The second part of the aluminium making is the alumina making, that is Al2O3, and the third part is the electrolysis of Al2O3 to produce aluminium metal. So let's talk about the making of alumina. So if I can write that this process that you see on your screen is we are trying to make here what we call as alumina from the bauxite ore. So what we will do is that we go through this flow sheet and also in the process see what are the various air polluting sources and what are the reactions, the chemical reaction that goes place. As you can see here, the mining is taking place for bauxite. So let's write here bauxite mining. Then it is transported to the alumina plant. Alumina plant can be far away from the bauxite mining area, or it can be very close to the bauxite mining area. There are many factors as to decide that where really the plant should really come up. But let's not get into the siting of the plant, but let's get into the more of the processing. Here the bauxite is transferred through the loader trucks. It could be the railway tracks, it could even be through the ship. But let's say the alumina, the bauxite which is here is brought to the alumina plant, and then it is dumped, and as you see that the loader is dumping the bauxite. So what happens as you are loading it here, there may be the emissions, okay, and the emission will be that of the dust. So wherever we see the dust emissions, we should think of the control. Let me make it a little better here. So here you have the emissions, and what emissions are really are that of dust or particulate emission. So there are various ways to how to handle the dust emissions. Either you can provide the fogging nozzles, or you can have little moisture content in there, or in fact you can enclose the entire area so that no dust comes out from there. And if you recall, in one of the lectures earlier we said that the fugitive emissions were of great significance. So we should, when we go to the plant and we are as a pollution control person, when we are planning the pollution control, we should just not look at the chimney. I tend to repeat this again and again, but because the fugitive emissions are sometimes very, very important and they cannot be ignored, and we should look at the emissions in totality rather than in just what is going through the process or going through the chimney. Nonetheless, the next step is through the conveyor belt. Okay, the conveyor belt also sometimes can be a little source of the emission of the particles, and then there is a huge area where the bauxite is stored. Okay, and again, if you recall, there can be some emissions from the bauxite storage area, as you can see, as I am trying to make the little drawing here for you. Okay, and finally it comes to the ball mill, as you can see here. So what we are really doing in the ball mill is the crushing. Okay, we are trying to crush the bauxite into I won't call it fine, but something like about 100 micron size, so that we can do the further processing of the bauxite. And as you can see here, after the ball mill, okay, the ball mill, once it is opened, this can also be the source of emissions. Okay, now once we have the bauxite after the ball mill, we kind of mix it with sodium hydroxide. Let's just underline it rather than circling it. Okay, here the sodium hydroxide which is added. We'll talk about what the use of the sodium hydroxide in a moment, but what you see here is along with steam the sodium hydroxide is made, and then what you're really getting here is the slurry of the bauxite, and with the slurry with the water and NaOH, which is the slurry that you are making it. So with this slurry is pumped into something called the digestion vessel. So let me indicate that what digestion. This is my digestion vessel, the container that you see, and in digestion vessel what happens is the digestion. But let me explain what digestion really is. So in digestion what we are doing is we are trying to dissolve the alumina part into the NaOH, and the other impurities will not be dissolved. So we are what basically we are doing is we are doing the phase transfer. Okay, so what happens is that once you have, if I can write the equation for you, is the following. Okay, so what we can do here is let's write that equation. Al2O3 XH2O was there, and I'm making it react with NaOH as I made the slurry with NaOH, and what it gives is in the dissolved form sodium aluminate. Okay, and this produces 2NaAlO2 plus what you will see, that amount of the water that will be taken out from there. So 1 plus X of water. So, and then to make this reaction happen we need high pressure. Okay, we need high pressure. Let me write pressure as P and high temperature, let's call it T. So those are the conditions that are maintained in the digestion vessel that you can see here, that is the digestion vessel. So what we have achieved with this process is that the Al2O3 we phase transfer it and make it dissolved and make the another compound here, if I can say, and this compound is in the liquid form. And like anyone else you will wonder as to what happened to all other impurities that we talked about. The other impurities were Fe2O3 and various silica, titanium, gallium, vanadium. The interesting part of this thing is they all will remain in the suspended form. So what we have achieved through the digestion is we are able to separate out the Al2O3 component, which is now in the liquid form in the form of sodium aluminate, whereas the rest of the impurities are in the suspended form. So what I can do now is to remove the suspended impurities. So the next step is what you see is the flash tank, okay, that you pass through the steam, and then now the flash tank you come to the blow off tank. Essentially it's a kind of surge tank which you can transfer the things here and then bring it to the various settlers, if I can call this, or clarification. Okay, you probably recall the clarifiers that we use or the clarification. Essentially what we are trying to do is separate out the solid, suspended solid components, which are the impurities. So basically what you see is the settling tank number 1, okay, and then it becomes concentrated here, the sludge, then it goes in here. This is the first one, the second one, and the third one. Okay, the design can vary, but the concept is that you are trying to remove all the impurities, and then once the crystal clear water is there, that is pumped into this one, and then on the second one and on the third one, and then finally a leaker, okay, which is kind of very clear, is taken further for the processing, so that you see the arrow after the removal of the suspended impurities, that the clear liquid is taken up. But you can also see all the impurities that we made them settle, okay, they become sludge, or in fact that we call as a mud, In fact, not only mud, we call that as the red mud. Okay, that you see here. The impurities are taken out as the red mud, and this is put through a system. In fact, we will call it red mud pond, or sometimes we will call it red mud lake, as you can see. So this impurities can go to the red mud. Okay, so let's get back to the process. After having dissolved the Al2O3 in the form of the sodium aluminate, as you see here, what happens to this one? There may still be some impurities. Okay, therefore what we do is we pass the liquor, the clearer liquor, with the filter press. This is my next step. Okay, filter press will effectively remove almost all suspended impurities. Okay, and once suspended impurities are gone, so again whatever is the impurities, that again is, you see here, that is again separated out, and that you can see here as the mud lake. And where this will be sent back? It will be sent back to the red mud lake. So that, so like this also is going to the red mud, this component here you see here, and this also is going to the red mud, because recall these are the impurities and that we need to separate it out. Well, from here, after the filter press, as you can see here, let me make this arrow here. Okay, where we take this one is to the precipitator. Okay, now after this point, okay, after all the impurities are removed, I have very crystal clear liquid, and which is largely sodium aluminate, or again I repeat, NaAlO2. So, but the idea is just simply not to stop at NaAlO2, but our objective is to form Al2O3. So, how that is done? So, that is done through the process called precipitator, or the where we can precipitate out, and you see here the whole column, as you can see here, is, that is what is called the precipitator. So, you can see here, let me mark it as the precipitator, and so if I can hatch it just to make sure that we understand. So, this is the precipitator. Once they, in fact, this liquor is also called pregnant liquor. Why we call it pregnant liquor? Because it's pregnant with the sodium aluminate. Okay, and now the idea here is to precipitate out the aluminum hydroxide, and we'll see as to how this is done. So, what I'll do is I'll remove this in the precipitator. Okay, what we do here is that this sodium aluminate, so let me write reaction here as to how this precipitation is made possible. What we had was sodium aluminate. Okay, if we add some excess water in there, or there is a water, okay, what we form is aluminum hydroxide. Okay, plus, let's not forget that we will recover the NaOH. Okay, let's try to balance this equation. How much will be the, okay, 2 sodium, so this has become 2 sodium here, and the aluminum is 2, so let's make this is 2 here. Okay, so what we are really doing is we are trying to precipitate this thing out. Okay, we started with sodium aluminate and we precipitate the aluminum hydroxide, and aluminum hydroxide are very gelatinous flocks, okay, that we can make it settle again. Okay, so what we are doing here is that we are making the aluminum hydroxide settled here. You see the little container here indicating that we are trying to settle, okay, settle the aluminum. So, if I can say that this really is aluminum hydroxide. Okay. Okay, let's see then where do we go from here. Sometimes we also need to, because this solution of sodium aluminate is supersaturated, so we put some seed here. Okay, seed that will help in the precipitation. So that what you say here, the ppt of alumina, or some seed is also added. So seed is nothing but again from the Al2O3. All right, now what let's again remove this. What now in the process what we have got is the aluminium hydroxide, and recall where we want to reach. We want to reach at the alumina, and what was alumina? Al2O3. So now we have to apply something so that we produce the Al2O3, and whenever there is a hydroxide and you want to get into the oxidized state, what we do is the process called calcination. So okay, so we'll do the same thing, calcination. This may be this may be moist, and aluminum hydroxide is passed through the. So what we do is go through the process called calcination. TION, calcination. And you see here how the calcination is done. We'll see in a moment that how the calcination is done, but let me write the reaction as to how the calcination will occur. And what we really need for calcination to be accomplished, we need to supply some heat. Okay, and if you apply the heat, the reaction that goes through is we get Al2O3, that is what we want to get, plus we should get the water out. The idea is to get the water out and get the calcined alumina. Okay, let's balance it. So this should be 2 here, and Al2 is fine, O3 is 6, hydrogen is 6. What if I put let's put what we had to put, need to put hydrogen is, how much hydrogen is 6, so let's put it 3. I think that sounds the balanced equation. So this is what is the thing which I wanted to achieve right from the beginning. That's what my objective was, and I'm able to do this one. And this, the interesting part is this alumina is about 98 to 99% pure. Okay, but we haven't looked at the calcination part, how this calcination is really done. Okay, here we have the aluminum hydroxide that is passed through the kiln. Okay, kiln are a rotating tunnel. Okay, let's make it a little rotating to indicate the arrow. The things are really rotating, and then we are supplying the heat through furnace. Supply heat, and most of the time we use the for the heating. Most of the time we don't use coal or something, because coal will make our alumina very impure. So what we use is generally, I mean again this varies from plant to plant, furnace oil or other cleaner fuel. Okay, so what you are getting here is in the kiln the heat is supplied, so aluminum hydroxide breaks down, or rather get calcined to Al2O3. But the moment we are firing a fuel, so there are emissions here. Okay, and what are these emissions? Because our focus here is to understand the air pollution aspect. So because you are firing the furnace oil, this can give little bit of it can give large amount of particulate matter. Which are the particulate matter? These particulate matters will be not from the furnace oil, but this will be the alumina particle matter, because alumina is produced and alumina will be in the very fine particles. Okay, so there will be particles that will be largely, let me write in the bracket so that there is no confusion, Al2O3. Then it can also produce significant amount of SO2. Why SO2? Because the fuel oil or the furnace oil that we are firing will have the sulfur, and that sulfur will be burnt out as the sulfur dioxide. So you can see sulfur dioxide. It has also been reported that little amount of carbon monoxide of the order of about 1% is also emitted, and of course the CO2 has to come out. Okay, and some very little amount of oxides of nitrogen are also expected, but this amount will be very, very small. So what you can see from here is again the rotary kiln. Okay, the kiln is nothing but calciner. Okay, and calciner is now become a significant source of air pollution, and this is the rotary kiln. so that there is an interaction between the aluminum hydroxide and the heat to produce Al2O3. So emission have to be controlled, okay, because emission control. Okay, emission control here has to be very stringent, very tight. You know, like we can't say, well, let's control 80% of it. No, because what we are really losing is the Al2O3 itself, which is my product. Okay, so the most of the plants will have the control. So control efficiency will be, if I can write the efficiency as sin eta, will be greater than 99.5%. So I want to capture everything, because if I don't capture, it's simply not only the pollution problem, but this also is the loss of the product. So normally what we use to control such a thing is we use the back filters as a control device here, or we can use the electrostatic precipitators, which I will write in the short form as ESP. So that very high efficiency control devices are used for trapping the particulate matter. So this is what is the final thing. And then once you are getting the calcined, okay, as you see here, calcined alumina, then you can send it to the, you can either ship it or transfer to the area where you have the aluminium plant, because this was the process what we discussed was the alumina plant. So finally it is shipped to the aluminium plant. So this is how it is. But let me also tell you a little bit that one point which we little missed here is that about the air pollution aspect is when you are doing the precipitation, things are open at the top, and once it's open, then you can also get the fumes of the NaOH fumes. Okay, and one more thing we must not forget is that once we are doing the precipitation, okay, we are recovering back NaOH, okay, and that NaOH is sent back to the in here. Okay, so whenever we are recovering the NaOH, which process we were recovering the NaOH, if you recall, whenever we were making the aluminum hydroxide here, the NaOH was recovered, and that recovered NaOH is recycled back to here, is recycled back to at NaOH as that you see here. So this is what is in brief the aluminium, or rather alumina production process. And so what we can quickly see is the sources of the pollution. That's what is interest to us. Source of pollution is, well, let me pinpoint for you. Source of pollution is this, okay, the dust emission. Source of pollution is the bauxite storage. Source of pollution is the also, let's not forget the conveyor belt. So we need to control all these sources. Okay, we can't say, well, this is not a major source. These are major sources. In fact, alumina plant not really very well maintained, is hugely dusty. Okay, and then again from that we also get some emissions from the flash mixing. We get the emissions from the precipitation area. We also get the and don't forget that we also get the solid disposal problem, that is from the red mud that is collected here. And sometimes the many metals, precious things are also recovered from the red mud area. Okay, so that kind of tells us the story of the making of the alumina, that is the Al2O3. And once we have made the Al2O3, the next process is of course making the aluminium, and that what we said, that aluminium is made through the process of electrolysis. So let's go through the next step. We'll see what this is. This picture, what you see is essentially, just to get you a little feel, okay, is the let's write it, red mud lake. See, there can be serious problem. This is a huge amount that needs to be disposed of, and the pH will be high, don't forget here, because we have been using the alumina. It will certainly be greater than 8.5 or something. Okay, and the disposal of this thing becomes a serious problem. There have been attempts to use this one for the road making, for the brick making, but still a method which is largely acceptable is still under the process. Now we'll begin with the making of the aluminium from alumina. So far we had seen that how the alumina, that was the Al2O3, was made, and there were certain issues, the environmental issues, the issue of air pollution from various stages, and then also there was the issue of the disposal of the red mud. But now we will begin from the point that we have produced Al2O3. As I said earlier, the process of making the aluminium out of Al2O3 is electrolysis. Okay, electrolysis. Let's write electrolysis. Okay, this method was developed in 1886 by two gentlemen called Hall and Herold. Okay, he was an American and he was a French. Okay, and they didn't know each other. That's a little interesting part. Independently they produced this method where they could make the aluminium from aluminum, and through the electrolysis. There the point was that Al2O3, okay, can be dissolved in something called what we call as a compound cryolite. It can be dissolved in cryolite. And what is cryolite really is? AlF3.3Na. This is the cryolite. Okay, they said if they could dissolve Al2O3 in cryolite, or let's call it not the cryolite but molten cryolite. Okay, when something is dissolved in something, okay, the electrolysis process can be used. Okay, so this once the Al2O3 can be dissolved into the cryolite, and in the molten cryolite we can proceed with the electrolysis. And the interesting part is that this Al2O3, okay, is can be melted at about 940 degrees Celsius. Okay, and then in this molten cryolite the Al2O3 can be dissolved, and then we can run through the process what we call as the electrolysis. Then let's talk about the electrolysis process. Al2O3 is in the dissolved form now, and we are going through the electrolysis process. It will produce aluminium, okay, and it will produce, let's also balance it as we go by. Okay, so we have the 6 here, so 2 will be here, so will be 4 here, aluminium plus plus plus. Okay, and this goes to the cathode as we said. Okay, and this goes to the anode, and this anode is made of carbon. So this oxygen, when it reaches the anode, it can react with this carbon anode and produce CO2. Okay, it can also produce CO. Balance that. Okay, these are the things. So what really you are seeing is that aluminium is constantly produced, oxygen is also produced. Oxygen is, let's write here so that we don't forget, is consumed at anode. So what we need to do is replenish vanish anode, because that is being consumed. Okay. So, this what is briefly like the process through which we can make the aluminium. Okay. So, if we can further divide the thing, that we need electrolyte cell, we need this process to go on. Okay. But we need to also produce anode, let us not forget that. Because why produce? Because anode is being continuously removed or continuously being consumed. So, when we are talking about the electrolysis, or we are talking about the aluminium making, it again divides the whole thing, as if we need two different plants. One is for making the anode, because anode is being consumed, okay, and one is the electrolysis process. So, what we will do is, first we will see the electrolysis process and come back to see how the anode is made. Okay. So, it might be a little interesting to see the electrolysis process inside the cell. Okay. So, this picture, as you see here, is the aluminum electrolyzing cell, and okay, this is what you will see as a pre-baked anode. I will explain you the meaning of what is this pre-baked anode really is, but let us little bit focus on this picture. And what you see here is the, okay, here is, first of all, this is the cell, okay, which is made of the cast iron steel shell. As you can see here, you can either be cast iron, it can be steel shell, and then you pass the current through this. Okay. So, this is the thermal insulation, as you can see, because we need constant heat here. So, the current is supplied, and then you see here, let me go one by one. You see here, these are the anodes. And these are the anodes. Okay. Okay. And this is what is called carbon lining, as you see here. That portion that I will try to show you this way is this one, is the carbon lining, and this forms what we call as cathode. Okay. And here what you see is the, let us make it here arrow, you have molten cryolite plus in that dissolved Al2O3. Okay. So, you can, and then the current supply for the anode is here, okay, and the current supply for the cathode is here. So, this is for anode, and this is for cathode. Okay. And this is, as I said, molten cryolite plus Al2O3. This is also, we can call this as, or we should really call this as, is the electrolyte. Okay. And what you see here is, now let's, and this white strip you are seeing is, will be what? Will be molten aluminium. Why we call it the molten aluminium is, you see here, this is the cathode or the carbon lining. So, aluminium will tend to go towards the cathode and the oxygen will tend to go to the anode. So, here is the oxygen that will come and attack here, okay, and here will be your aluminium that you will get in the at the cathode. Okay. So, this is the process, but the other thing which we need to see really is that in the center, okay, this is where you are trying to put your constant supply of Al2O3, because that is continuously consumed, that is continuously used up to form the aluminium. So, here what you see here, as we are putting the Al2O3, okay, Al2O3 gets dissolved, and partly it will make little crust on top of this one. So you can see it's a crust, and the crust, you can see that as the alumina crust. So whole thing tend to be covered fully, okay. And then whenever you want to supply Al2O3, what you do here is you bring this, what is called crust baker, you break the things and put the alumina down there, and this as you see a little thing here, the whole thing is filled with Al2O3. So first you break the crust and let this kind of hopper kind of thing you see here, that alumina is dropped in there, okay. Once the alumina is dropped, it will dissolve into the cryolite and make electrolyte. The electric process will go, and there will be production of the aluminium, and the oxygen will be going to the anode, and this anode, which is made of the carbon anode, which will be continuously be consumed here, okay. And then you call here the other thing, the whole thing is covered by the hoods, okay, see here, okay. And this is also my, as you can see here, this is also my cover. In fact, this cover can be removed, okay, because we need to do some operation in here, then we can remove the covers. The other thing what you see here is the fume collection system, okay. It will become little clear in a moment when I will show you the another picture. So here there is a lot of possibility of the emissions occurring here, because we have the high temperature. We also have some of the volatilization of the fluoride material, and then these fluoride material can really tend to go out as soon as, especially the emissions are very large when the crust is broken, because the whole thing is opened up. As a result, there will be emissions. So we'll talk about the emissions in a moment, but here what you have to remember is this is the electrolysis process that is going on, and the anode is being consumed. And here what you see here, the anode, which is this thing, is already pre-baked. It is in the solid form. Something is baked, you go to the bakery and you find the solid things which are baked, so like biscuit, it's baked, it's not a paste. So that's what is called already baked, so we call this as the pre-baked, okay. So but why we need to say the pre-baked? Because this system, what I'm defining to you right now, is a pre-baked anode, but there are the technologies where anode need not be pre-baked, and we'll see those things in a moment. And let me see if I can give you a little picture from let's see this picture. This picture is taken from the internet, and you see this is the aluminium plant, and these are the what, if I can draw a line here, are, we call them as pot line, because here we have series of electrolyte pots. I can also show you the perhaps little bit okay, again this is more of schematic. This is a little picture from inside, and what you see in this here, okay, these are the various cells, okay, electrolyte cell, and the whole thing is connected in the series, okay, and the current is being supplied. To give you a little feel as to how much is the current that it needs, okay, it's current. It can be anywhere from 100 to 200 or 250 kiloamps. This is to give you a little feel as to, with the regular power supply, what you see in the houses is hardly 5 amperes or 15 amperes, but the kind of electrical energy that we need to produce the aluminum is a huge amount of energy that we require. So the current supply is here. These are the, and if you, as I had explained to you earlier, these are the covers or hoods, okay, that can be removed, okay. These are the whole thing, if I can show you, they are the anode holding rods. Okay, and then whatever the operation that needs to be done is the crane is moved. As you can see, the big crane here that moves through the pot room, okay, and the operations are done in the individual pot. And you also see that some of the operations can be done by opening the hood here, and then there is a the machine which can also be hooked to the crane, and these are the thing. And you can also see there is some dusty conditions and some emissions are there, and for those emissions we will talk in a moment. To give you a little feel that how much is the energy that is used up in the aluminum making. Okay, this also makes sense because whatever is the energy, the electric energy that we make, that is also source of air pollution. So this the success of the operation of the plant, both from the pollution point of view as well as from the production point of view, is the energy that you consumed. And this little figure, you see that this is the kilowatt hour of the energy which is used for the per ton of the kilogram of the aluminum produced. I think this is kilogram of the aluminum produced. See here, like in earlier processes that use huge amount of energy, here you see here, and there have been more and more technological development, and this energy requirement has brought down to a very significant thing. So the company which can produce aluminum with the less energy consumption, or the cost of the energy in the company where the cost of energy is low, they will produce a profitable aluminum production that you can see here. You can also estimate, let's quickly do that. Suppose you want to see change in aluminum price if power cost is up by 10 paisa, small amount, 10 paisa. Okay, and suppose your plant is operating at these conditions, so you are using 20 kilowatt hour per kg, let's say. So the cost that will go up, the 20 into per unit 10 paisa is up. Okay, so this is so much of paisa, and then you want to find out for the per ton. Okay, so you multiply this one and divide by 100 because you want to get the rupees, and then you say this goes off in there, and then you have 2000 rupees per ton of aluminum. I think we did it correct. So just get a feel, you know, like if the rise in the cost of the electricity is 10 paisa per unit, and that may result in the cost up for the aluminum by about rupees 2000 per ton. That's very, very significant amount. Well, let's now talk about the anode baking. All right, if you recall, we were having in the aluminum production, we had the electrolyte cell, and in the electrolyte cell there was an anode. Okay, the anode was continuously consumed because the oxygen was consuming the anode, and finally what we are producing was CO2 and oxygen, CO2 and CO sometimes. So let's have a look at, we need to have the anode making as well. So anode making is an integral part of aluminum production. So what we will discuss here, the flow sheet that you see here. I'll go over this flow sheet to make you explain as to what is the anode making really means is. As you can see, the anode is made of carbon. So we start with the petroleum coke that we get from the refineries. So this is the solid form, this is crushed, and the moment you do some crushing, so particulate emissions are there. So you can see again the dust emissions, and they need to be controlled either through cyclone or back filters. Okay. Once the crushing is done, it's very important that when we are making the anode is in fact is various sizes that we need to make the anode with. So we have basically a process called the size selective sorting. Okay, So as we do the sieving, for example, to sort the various particle size, so it is essentially sieving that we do, and here also as the sieving is done, lot of particles that comes out, that is of the petroleum coke. So again particulate matter and must be removed by the means of cyclone. Okay, and then once the selective site sorting is done, we need to finally make the anode. But you see here the petroleum coke doesn't have the quality of binding itself, so we need to put some binder. Okay, that binder is we call that as a pitch. Okay, again from the petroleum refinery it can come, or from the other sources. So here you see here pitch is used for the binding the petroleum coke to form the anode. But before the pitch can be used, pitch is processed through the crushing operation, as you can see here. Okay, and again the moment you see the crushing, there are a lot of particulate matter emissions. Okay, and after the crushing is done, it is mixed or blended with the petroleum coke, which are already in the fine particulate form, and then you supply some heat here, as you can see, because both are kind of made viscous, and then this kind of we get the heated blending here. Okay, so you have a reasonably good paste that you are getting here, but then we can't stop the operation here, because we need to make the pre-baked anode, because the baking has to be done. So what we do is then we pass this material in a particular shape, okay, to the anode baking surface furnace. Sorry. So here you see the anode baking furnace, as you can see here, that I have drawn for you. Here what you do is that when for the baking you need to supply the heat. Okay, the heat is supplied through the combustion of the fuel oil, for example. So let's write it here, so there's no confusion. Fuel, it can be fuel oil, okay, or heat. But remember that this flue gases from the fuel oil does not come into direct contact of the paste anode. See, otherwise the anode will start burning itself. So it is an indirect heating, you know, like at one point there is a block of anode, and there is another conduit or the pipe which is carrying the heat. So indirectly the anode is heated. Once it is heated, it is baked. Once it is baked, then it is in the solid form. But in the process of baking, lots of emissions occur. So once emissions are called, one emission will be the combustion related emissions that you can see here. Because why combustion related? Because we are burning the fuel. So what you will get here is, don't forget, you will get the CO2, you will get some amount of the sulfur dioxide, because the sulfur can always be present in the fuel oil that you can see here. There can be a little bit of NOx also, although it is very controlled firing, so you can get some NOx also, and not so much, but maybe at times you can also get the particulate matter. That is one side of the story. The second side of the story is that once we are having the coke, which is here, that came in the process, and you are having the pitch that came in the process here, there also the impurities which are there are emitted. Otherwise these impurities will go in your cell, in the pot line or in the pot. Once it goes in the pot, your aluminium production, the quality of the aluminium will go bad. Okay, so what happens is that once you are heating it up, see, I am not calling it the firing, it's the anode, paste form, the anode is being heated up. So whatever is a volatile organic compound, sorry, that you see here, the VOCs will be emitted. VOCs can be benzene, toluene, or other organic compounds which are in the volatile phase, that will be emitted, which are very, very harmful. You can also emit from this process is some of the PHs can be emitted, polycyclic aromatic hydrocarbons. Some of the hydrogen sulfide, which, because the coke will have high amount of sulfur, the pitch can also have the sulfur, as you can see. So some of the H2S will also be emitted, and apart from that, some amount of hydrogen fluoride acid, okay, HF can also be emitted. One can ask why the HF here or the fluoride, she recall that the used up anodes, okay, used up anodes are also recycled in the anode baking plant, and these anodes are, in a matter of fact, then these anodes were in the pot, and in the pot we are using a lot of fluoride, and that fluoride will somehow become part of the used up anode, and then once they are brought up and then used again, the sum of the fluoride emission can also takes place. So you can see here that which has very high potential of the air pollution, and this pollution, not only the high potential of air pollution, this also has the potential for very carcinogenic toxic compounds which can cause serious problem in the environment. So you can see the anode baking processes, the emissions from the anode baking. Then you can also see that this also causes the problem with respect to the emission of carbon dioxide, sulfur dioxide, NOx, and some amount of the particulate matter. Anyway, once this anode baking is done, as you can see here, these things are supplied back. They need to be taken to the pot where they will be used in the electrolysis and form the anode. So if I can say this is my one pot here, okay. So the anode is used up here, okay. Then what else we need to go? The electricity need to be put in. Cryolite, okay, here is the cryolite need to be put in, and so is the alumina constantly need to be put in, and this all the process, okay, apart one side it will give me the aluminium, no doubt about it, that's what is my objective is, but this process also gives me some kind of emissions, as you can see here, okay. And these emissions are very I'll explain you in a moment. These emissions are generally fluoride emissions, fluoride, okay. And if I can go to the next slide. These fluoride emissions, we will see how these fluoride emissions occur. So having said that you need an anode baking plant, some of the technologies they don't do the anode baking here, okay. If I can show you that right from this thing, okay, let's make this line as a dash. They don't do the anode baking, but they use the paste, and then the paste itself, as you can see, this is the paste that I am taking up, is put in the pot. So some of the technologies they are avoiding the anode baking itself. Why they are not avoiding the anode baking? The argument is that in the pot the temperature is high, okay. So that the high temperature itself will be enough to make that paste in the solid form, and that technology where they are using the paste but not pre-baked anode, that technology is called Soderberg technology, okay. So if what I'll do is then I'll remove this this stuff here. All right, you see here in this process we are not baking the anode previously, but in fact the paste itself, as you see here in the dash form, is sent to the pot, and then this is the this method, okay, where paste of anode is used. This is called Soderberg in Norwegian, based on the technology given by one Norwegian. It's called Soderberg technology. And what you see in the Soderberg technology is that hoping that whatever is the paste of the anode is directly put into the pot, and then hopefully in the pot, or in fact it is solidify, and the baking takes place inside the pot. So we are using the heat available in the pot to do the baking of the anode. But then in the process, once we are doing the baking here in the pot room, because the emissions will also be that of the VOCs, okay, because the baking is being taken place inside the pot. So inside the pot room there will be emission of VOCs, the pHs, some of the H2S. Okay, so this becomes very serious problem in the pot room. But right now the people you are using the technology is more of pre-baked technology. So far what we have seen is the aluminum production. The first is aluminum production we did the aluminum production, and we went through the electrolysis process. And in the next lecture we will look more into the emissions, how it happens and how that can be controlled.